My name is Sandeep Bhatia, Assistant Professor in the Department of Electronics and Communication Engineering at Rajkumar Goyal Institute of Technology, Ghaziabad. So, in a series of lectures delivering for a subject Microcontroller and Embedded Systems Design, having code KEC 061, what we have covered, we have completed our unit number 1st and 2nd, and in the previous lecture we have started with the unit number 3. So, in a half portion of unit number 3, it is all about the embedded system. So, in the previous lecture we have covered some basics of embedded system, introduction of embedded system, what are the applications of embedded system, and in the at the last of previous lecture we have discussed some real time applications of embedded system, that is gasoline control unit. So, in this lecture, that is the part 2 of embedded system, we will discuss these just a second. We will discuss these table of contents, these things. First one is the building embedded system using microcontrollers, how we can build any embedded system, options for building embedded system, what are the various options, what are the various criteria to build any particular embedded system, we will discuss in this topic. What are the building blocks of any embedded system hardware, what should be the main building blocks used in any particular embedded system application, we will discuss in this topic. After that, build process of embedded system, what should be the build process to design any embedded system. Okay. Design process used in any embedded system, what should be the design process we can use in embedded system, what are the structural units in embedded processor. So, we will discuss these table of content in our today lecture. Okay. So, first topic is building embedded systems using microcontrollers. Okay. So, in most embedded systems microcontrollers are to be chosen for the best solution, since they offer. So, why we are using microcontrollers in any particular embedded system, because it has a low development and manufacturing cost. With the microcontrollers, the development cost is low and manufacturing cost is low. This is the main requirement, because if the cost will be more, nobody will buy it. Okay. And easy porting and updating. So, by using microcontroller, it is easy to upgrade, easy to port, and easy to interface the devices. It has a light footprint. Light footprint is basically it provides low cost solutions to the processor. Okay. So, light footprint provide a low cost processor. We can say that it is a hardware and software. So, hardware and software means that it can take less memory space. So, if we are talking about the hardware, that is power units, we can say that RAM or ROM, it can take less space in the memory, and software also take less space in the processor. Okay. So, these are the light footprints. Relatively low power consumption. By using the microcontrollers, the power consumption is low as compared to general purpose system. Satisfactory performance for low end products. What is the meaning of the low end products? Low end products are those products which provide low cost, more reliability, less power consumption features in our final product. Okay. So, low end product means that the end product we are launching into the market has a low cost, more features as compared to other systems. So, here this is the processor, it is a Freescale ARM processor. So, this is the processor chip we can use in our embedded system. Okay. So, next topic is what are the options, different options for building any embedded system. What are the different options available to build any embedded systems. Okay. So, here I am taking some table. In this table, first is the implementations, that is the options. We are talking about the options, these are the options: discrete logic, ASIC, programmable logic. So, these are the options available to design any system, and we are comparing these options with the different parameters in terms of cost, unit cost, upgrade, size, weight, power, and system speed. So, options are this, and we are comparing these options in different parameters. Okay. So, first option available to design any embedded system is discrete logic. Discrete logic with the discrete logic means general logics, general components. By using general components, we can design our embedded system. Application specific integrated circuit. ASIC means that application specific integrated circuits. Basically, these are the integrated circuits, and these are used in embedded system to do a particular task. If we want we want that our embedded system will work in a particular application, and it can carry out specific application, then we will use ASIC integrated circuit. Okay. So, these are the general integrated circuit, this is the application specific integrated circuit. Our next option is programmable logic devices, FPGA. FPGA means that field programmable gate arrays. Okay, and PLD is the programmable logic devices. These are the options available to build any operating system. Next one is the microprocessor plus memory plus peripherals. So, what does mean, what is the meaning of the plus? Why we are adding plus here? Plus here means that microprocessor is a general purpose CPU only, and it did not have any memory. So, plus means that we are adding external memory and peripherals to the CPU, that is a microprocessor. That is why we are representing plus here. Microcontrollers, next option in microcontrollers, INT means it has an internal memory and peripherals. So, in case of microcontroller, memory, RAM, ROM or and peripherals like ADC, DAC timers all are integrated on the same chip. So, that is why we are not representing plus here. Okay, we are not representing plus here. Next option available is the embedded pieces. Embedded pieces means that embedded programmable controllers. Okay. So, we are comparing these options with the different parameters. Okay. So, first one is the design cost. By using general purpose system components, the design cost is low, unit cost is some in middleware. Upgrade, it is hard to upgrade the discrete logic devices, general logic devices. Size is large. By using the general purpose component, size will be large. Weight is high as compared to other components. Power is somewhat difficult to calculate because it may vary. It may be low, it may be mid, average, or it may be high. System speed is very fast by using discrete logic components. Okay. If we are talking about the ASIC, application specific integrated circuits, the design cost will be high as compared to general systems. Unit cost is very low because of we are using specific components according to the application. Okay. It is hard to upgrade it. Okay, because once it manufactured by the any company or any industry, it is hard to upgrade any particular device. Okay. It has a teeny one die size, it is very low in size, weight is very low because we are using lesser components and we are using components as per our application need. Power is low, it is extremely fast. Okay. So, programmable logic FPGA PLD, it also has a design cost is low, unit cost is mid in some in the average, we can say that cost is not more. It is easy to upgrade by using FPGA PLDs. The main feature is that, main advantage is that it is easy to upgrade the environment, easy to upgrade the applications. Size is small, weight is low, and power requirement may be vary from medium to high, and system speed is fast. By using the microprocessor plus memory plus peripherals, design cost may vary from the low to the middle, unit cost is middle, it is easy to upgrade, small to medium size, low to moderate weight, it is medium power and moderate speed. By using the microcontrollers, it has a low cost and unit cost vary from middle to the low, it is easy to upgrade the system, it has a small size, low weight, medium power and slow to moderate. Speed is varying from the slow to the moderate. By using embedded PCs, cost is low, unit cost is high. Okay. It is easy to upgrade the application, size is medium, moderate to high weight and medium to high power consumption, and the speed is fast. So, these are the different options available to design any particular embedded system. Okay. So, in next slide we will see the building blocks required to embedded system hardware. So, what are the various building blocks required to design any embedded system? So, first one is the power source. This is the general requirement, because without power source any application cannot be run. So for any application of embedded system, we need power source to run it. Okay, it is the main requirement. After that, clock oscillator, it is also a main requirement, because to trigger any because in a embedded system there are various integrated circuit chips. So to trigger any particular chip, we need some frequency operation, and who is providing frequency operation? Clock circuit will provide the frequency of operation. So this unit will provide the frequency operation to run any particular IC. Okay, we have a system timer. It may be a we need timer and counters to carry to counting the events happening inside or outside the microcontrollers. So timer is also a main unit. We are talking about the some general building blocks in a embedded system. We have a real time clock, RTC clock, to display the numbers, times, date, etc. It has a real time clock. It has a reset circuit. Reset means when once we press the reset button, or we are using reset circuit, it will initialize to its beginning value. Okay, it will go into its initial values. Power up reset circuit, here we can use brownout reset circuit. In previous lectures we have seen that what are the power reset circuit. We can use watchdog timer reset circuit. Watchdog timer means that it reset or restart a system in case of any software fault or errors, bugs. Okay, memory we can use, it may be a RAM or ROM. Input output ports we can use, input output buses we can use. Okay, input output interfaces, DAC and ADC. So we are not limited to this. There are maybe many building blocks in any particular embedded applications, but these are the general ones. Okay, and these blocks may be increase or decrease according to the particular applications. Okay, so these are the building blocks required to design an embedded system. So the next topic is build process. What is the build process to design any embedded system? So the build process is the we can say that the first step to build any embedded system is to selecting a processor, because you need to select a processor which processor is compatible with our particular embedded system application. Okay, so first step is to select a processor. After selecting the processor, so what should be the considerations we need to take care while selecting the processor? So the selection of a processor will be based upon the instruction set it's posed. It may be a RISC instruction set, it may be a CISC. Okay, RISC means reduced instruction set computing, and CISC means a complex instruction set computing. So instruction set, how many instructions it can carry out by any processor, it is the main parameter. What are the number of bits it can handle, what is the maximum bits it can handle, it is also a build process, it is also a main feature of while selecting a processor. Clock frequency, which clock frequency it can support. Processor, it may be a megahertz, it may be a gigahertz. So it can carry out million instructions per second. So to select any particular processor, the next feature is ability to solve complex algorithms. So while using any processor, can it handle complex algorithm? So it is the main criteria while using processor. So it is used in meeting the deadlines for their processing. Okay, so these are the things we can take care while building any embedded system. Okay. So the build process for embedded software consists, in the previous slide we have talking about the build process in terms of processor. Now we are talking about the build process in terms of software. So in terms of software, it has a project file consisting of source file and library files. So while running any particular software application, it may have a library files, it may have a source files. Okay. Compilation of the project files, how to compile the files, what are the library files we can use in any particular applications. Okay, linking of all the object files into onto a single relocated object file, it is also the main feature while for software. Okay, converting the object file into a hex file to binary image. So all these operations can be carried out by embedded system. So these are also a constraint while designing any embedded system. Okay. So software, what are the different software we can use? We may use high level languages like C, C++, .NET, Java or Pascal we can also use. We can use also as embedded language, assembly language as well. Simulators we can use Atmos, Studio, MASM. We are not limited to this. There may be many simulators. Compilers we can use Keel, write compilers, etc. Okay. So these are the build process, starting from the compiler. What a compiler will do, it will convert the C program into the assembly language program. Okay. And the assembler will convert the assembly language program into a machine language program, machine language. So assembler will convert the assembly language into the machine language. And what the linker will do, the conversion take place by the assembler from the assembly language to the machine language. It will further linked by the linker into the machine language program that can be executable, that can be executed. Okay. And after a loader will load the executable machine language program file into the final memory into the that is a processor, embedded system processor. Okay. So these are the various steps used in our software while designing any embedded system product. Okay. So this is the design process, this is the basic design process. So concept used during design process, what should be the concept used while designing any embedded product? Abstraction of stages, abstraction, hardware and software architecture. Okay. Extra functional properties, system related family of design, modular design, mapping, what should be the mapping, what should be the layout of a design, user interface design. Okay, refinements. So these are the basic steps. We will not go into the depth of these topics because we have to just see what should be the design process. Okay. So these are the development process, model, design, implementation, testing. These are the linear sequence. We are not limited to these are the basic design process. Okay. So what should be the design matrix for designing any particular application? Design matrix is power dissipation, performance, process deadlines, size, user interface, size, engineering cost. Here we are talking about the recurring cost, or we can say non-recurring cost, non-recurring engineering or cost. Manufacturing cost, flexibility, prototype development time, time to launch the product into the market, system and user safety, maintenance. So let us take first is the power dissipation. So while designing any process, we should take care of the power dissipation. Dissipation should not be more in any particular embedded application. Second one is the performance. It should have a high performance. It should have a reliable performance while working on particular any applications. It should meet the deadlines. That is the process deadlines. That is, it should meet the deadlines. Because if it did not meet the deadlines, we cannot run any particular applications. If we are talking about the car or washing machine, if it works on the, if it not meet the deadlines, then why we are using these particular embedded applications? So it is the main feature. User interface, size should be less, or size should be compatible with the particular applications. If another company are designing any embedded system, if it is a less size, compatible size with the customer, and if company A is launching the product into the market that has a large size, and the size is not compatible with the customers, then what will the customer will do? It will purchase the device, embedded device which has a compatible size. Okay. Engineering cost should be less, that is a recurring cost or non-recurring cost. These are the things we have to take care while designing any product. Manufacturing cost should be less, that is a marginal benefit should be maintained. Okay. Flexibility, it should be flexible with the our environment. Prototype development time, that is the development type of the product should be we can say that should be limited. Within a limited time frame, we have to design our product. Time to launch the market, time to launch the final product into the market, we have to also take care while designing any system. System and user safety, it should have a system safety features. Okay. Testing phase include this. Maintenance time. So all these are the design metrics while designing any embedded system product. So these are the, we are discussing these design metrics, we are inculcate these design metrics into this one. These are the general steps we have to take care while designing any system. So this is a top to down approach. Okay. So what are the various abstraction of steps? First one is the requirement, second one is the specifications, third one is the architecture, fourth one is the component, and fifth one is the system integration. Okay. So, I am taking real time example. Let us take washing machine. Okay. So, if we are talking about the washing machine, that is a embedded device. If we are going to design any washing machine by any company, then the first one is the requirement. What should be the requirement? What is the requirement of the user? So, we have to survey the market. What are the requirements? So, what are the need of the system? So, requirement is the first step. We have to take care that what should be the requirement of our system, and after requirement we will see the specifications. In these specifications we will just gather the components, gather the data while designing any product. After that, the architecture basically the layout of the product, design process of a product. Here we are talking about the layout, how the components can be placed in any layout. We are talking about in step number 3rd. And after that, the components. What are the components? What are the different components can be used in our embedded system? It may be a hardware component, it may be a software compatibility. Okay. After selection all these things, we are integrated our components into the system. Integration means into our processor or IC. System integration means that what are the we have designed the system, we are finally integrated into the final chip after testing verification. So, these are the general design steps. Okay. So, our next topic is the structural units in embedded process. What are the structural units? We have seen the design process, we have seen the build process. Now, the question is what should be the various structural units can be used in any embedded process. So, this diagram represents the structural units. This is the basic diagram. Here you can see that we have a processor, control unit. Okay. So, all these blocks are connected by internal buses. These are the buses. These are the buses. Buses carry data from one block to the another block. Okay. So, here you can see that here this is the instruction queue, instruction register, instruction decoder, control unit, advanced processing units, SRS, ARS, FRS, okay, register set, advanced register set, specific register set, ALU, arithmetic logic unit, floating point unit, okay, data instruction cache, okay, data cache, prefetch control unit, memory management unit, program counter, memory address register, stack pointer, memory data register, bus interface unit, and address bus, data bus, control bus. So, there are many components in any processor. These are the basic components. Okay. So, let us discuss one by one. First one is the internal buses. What is the function of the buses? Buses carry data from one end to the another end, another device. Okay. All the system buses, all the units are connected through the buses. So, buses carry out data from one device to the another device. Its bit may be vary, it may be 8, 16, 32 or 64 bit. Address bus. Next one is the address bus. What is the function of the address bus? Address bus is a unidirectional. So, CPU communicate with the peripherals by using the address bus. So, it plays the address of the particular peripheral to which to whom it is communicating. Okay. So, it is a unidirectional. So, it is in the form of we can say that memory address registers. So, next one is the data bus. What is the function of the data bus? It is a bidirectional. So, data bus is used to carry the data from the one device to the another device in between the communication, okay, in between the devices. Next one is the control bus. Control bus carry out the control signal between the processor and memory devices. After that, we have a bus interface unit. Bus interface unit, it is the interface unit between the processor internal units with the external buses. So, if we want to communicate the internal units with the external buses, this will be carried out by the BIU. Okay. Here we can see that this is the BIU. So, what is the function of the BIU? All the internal system, all the internal devices are communicating with the external devices by using the BIU. Okay. After that, we have a memory address register. What is the function of memory address register? It is directly linked with the address bus. So, basically it is it hold the address of the byte, or byte means 8 bit, or word means 16 bit. So, it hold the address of the byte or word to be fetched from the external memories. From the external memory, if you want to fetch any data, MAR hold its address. After that MDR, it hold a byte or word fetched from external memory or input output address. It hold the address, it hold the data. What is the function of the program counter? Program counter point to the address of the next instruction to be executed by the any processor. Okay, so it hold the memory address of the next instruction that would be executed by the processor. Stack pointer means that it is used to point out a stack of the memory location. So it is a pointer for an address which corresponds to stack top in the memory. So basically, if this is the memory, in memory there are many stacks. So at the top of the stack, or this is the bottom of the stack, so stack pointer will point out the top of the stack to point out the memory location. Okay. Instruction register basically it is a register which can store many instructions on a temporary basis. So it takes sequentially the instruction and codes to the execution unit of the processor. So the fetching, so if we are if any processor fetches the data from the buses, it will store this into the instruction register. Okay. So after that we have instruction decoder. After instruction register, the instructions will be decoded in the instruction decoder. So it decodes the instruction opcode received at the IR, passes it to the processor. So here you can see that instruction register will store the registers and it will be decoded into the ID unit. Okay. So instruction queue, it is the queue of instructions so that the IR does not have to wait for the next instruction after one has to be carried out. So in a instruction queue means that instructions are in a queue. If one instruction is to be carried out, another instruction is ready to execute. Okay. Arithmetic logic unit, it can carry out the arithmetic operations like subtraction, multiplication, addition, division, multiplication, division, etc. Okay. It has a logical, can do logical operations like and, or, etc. So it is a unit which is used to execute arithmetic and logical operations according to the current instruction present in the IR. After that we have a floating point processing unit, FPPU, a unit separate from ALU for floating point processing, which is essential in processing mathematical functions fast in microprocessor or DSP. So this is the floating point unit. Here you can see that floating point unit. So we can see that this is the floating point unit. Okay. So this can carry the operations. After that we have a floating point register set, a register set which is dedicated for storing floating point numbers. Floating point numbers means that 1.6, 1.8 in a standard format and used by the FPU for its data and stack. After that it has a control unit. Here you can see that FPPU, and this is the control unit. Control unit will it is connected in between the instruction queue, instruction units and main unit, that is the SP. Okay. So control unit is you can, in this diagram you can say that control unit is connected to every block. Okay. It is carry out the control operations. So it controls all the bus activities and unit function needed for processing. After that we have a memory management unit. Here it is a concept of paging segmentation. Memory management unit will take care the memory allocation, deallocation. If any memory is unutilized, it can pass that memory to the next stack. So memory management will be taken care by the memory management unit. It manages the memory such that instruction data ready available for processing. Application register set, it is a set of on-chip registers used during processing the instruction of the application program of the user. Application register set. Okay. Instruction cache, what is the meaning of the cache? It is the fastest memory. So it can, on temporary basis it can hold the data. So it sequentially stores like an instruction queue the instructions in FIFO. It works on the FIFO manner, that is first in first out. It has a data cache for pre-fetching of the data from the external memory. So data cache generally holds both the key and the value together at the location. It has a PFCU unit, prefetch control unit. Prefetch control unit means pre-fetching of the data will be take care by the prefetch control unit. So it after prefetching of the data, it this data go into the iCache unit and decache in advance from the memory unit. So the instruction and the data are delivered when needed to be processed in execution unit. So all these blocks are can be integrated on a single system. It has a register window as well. It is basically a subset of registers which has meaning of the registers. Okay, it has an advanced processing unit for multi-stage pipelining and to obtain processing speed higher than one instruction per clock cycle. So, it has an advanced processing unit to carry out the advanced operations. Okay. It has atomic operation unit. It lets a user instruction when broken into number of processor instruction called atomic operation. So, atomic operation means user instruction broken into a number of processor instructions to finish before an interrupt of a process occurs. So, these are the various things can be inculcated in any embedded system. So, thank you everyone. I hope you have enjoyed my lecture. Thanks for your patience.